This video will cover section 4.2, Trigonometric Functions, the unit circle, and it is for my 2412 class. The objectives for this section will be to identify a unit circle and describe its relationship to real numbers, to evaluate trigonometric functions using the unit circle, and to use the domain and period to evaluate sine and cosine functions, and to use a calculator to evaluate trigonometric functions. So as we introduce the concept of the unit circle in the previous section, we just referred to it as a circle with a radius of 1. And so that is exactly what it is. But now we're going to define it with the equation of a circle. And from pre-calculus 1, if you don't remember that, it's okay. The equation of a circle is defined like this. And so with r and being the radius, and in this case, our unit circle has a radius of 1. And that's why we call it unit circle. So 1 square is still 1. Now for h and k, the letters that we have here, they represent the shifting of your circle with respect to the xy axis. So ours is going to be center at the origin. And for that reason, both h and k for the unit circle, they equal to 0. So the center, not the vertex, the center is at 0, 0, which is the origin. Okay, so that is what we consider the unit circle. Now, if we actually plot that on the Cartesian plane, we will see that in each direction, right, left, up and down, or north, east, south, and west, since the radius is always equal to 1, and if we speak about it in terms of absolute value, distance, like that, it will always be positive, right? The absolute value of 1, it will still be 1. So the distance it's always positive, so the radius is equal to 1 here and here and here and here. And so for that reason, you can see the coordinates of the points that are actually on the circle. They are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Now, just to review from the previous section and to remember where those radians were located at, if we talk about angles, that was 0 radians. The one up here, 90 degrees or pi over 2. And if we go 180 degrees from the positive x-axis, we will have 180 degrees, which is equivalent to pi radians. And if we go 3/4 of a circle, that is 270 degrees or 3 pi over 2 radians. So imagine that you are wrapping the real number line, a straight line, around the circle. So this is a straight line, and imagine you wrap that or you curve it so that it fits the circumference of the circle. And if we do that in the counterclockwise direction, remember that's opposite than the clock, we will have positive numbers for our angle. And if we do that in the opposite, the same, this line, if we wrap that around the circle, but now starting from the x-axis, but now in the clockwise direction, we will have negative numbers. And we did mention that on the previous video. Okay, so here we're going to refer to the central angle with the Greek letter theta, but to the sector, not the sector, the arc length that would be equal to t. And so if we go again in the counterclockwise direction, t will be positive. And if we go clockwise direction, t will be negative. In both cases, the circumference will be 2 pi r. In general, each real number t, remember that was the length of that little portion of the circumference, the arc length, also corresponds to the central angle. Central angle is an angle whose vertex is at the center of the circle. And the central angle is being labeled with the Greek letter theta. And it is in standard position, and the radian measure is equal to the arc length. So we were in fact using this formula in the previous section, and S is the arc length, R is the radius, and theta is the measure of the central angle. So if R is equal to 1, so I'm going to replace R with the number 1, it will be 1 times theta, so that will equal to S is equal to theta. So that indicates that when the radius of the circle, and that's why we need a unit circle, and that's why we define it that way, is when the radius is equal to 1, and then both the center angle and the arc length will be of the same exact measurement. Now, if the radius is bigger than 1, they will not be equal. The length of that intercepted arc will not be equal to the angle measurement of the central angle. However, we do have something called similar triangles, and based on those, the properties, all of the properties that we will be using will still be valid. They will be derived using the unit circle, but we could extend it to any type of triangle, and that is something that we will do in the next section. So going back to this definition, I will finish reading this slide. So it indicates that the real number t is the directional length of the arc intercepted by angle theta, and it's also given in radians. Remember, every time you use this formula, you must have your angle measure in radians. From the preceding discussion, it follows that the coordinates x and y are two functions of the real variable t. And this is going to become very important when we define the domain and the range of this function, because it will be based on the letter t. And just for a minute, we're going to stop using theta because we're moving from the central angle, which was labeled as theta, and we are extending the concept to the intercepted arc. So we are going to use the coordinates x and y to define sine, cosecant, cosine, secant, tangent, and cotangent. So for sine, and if we were just using, imagine that you have a circle here, and we just happen to have a point here. And so for that point, we're going to give it the coordinates. We don't know what they are, so we're just going to call them x and y. And so right here, what we're going to do, and in this little the red one will be the radius. So for sine, we will be using the coordinate y. So we will say sine of the angle t is equal to y. Now for cosine, we will be using x, the coordinate x, and for tangent, that one will be equal to y over x. Now, cotangent is the reciprocal of tangent, so that one will be y over x. For secant, this will be the reciprocal of cosine, and so that one will be equal to 1 over x. And finally, for cosecant, we use the reciprocal of sine. So if sine was to have a 1 under for the denominator, cosecant will be 1 over y. And in the following sections, we will extend the concept, like if the radius was not the radius of a unit circle, so if the radius wasn't equal to 1, and so we could say that the sine will be equal to y, the y coordinate over r, and so then cosecant will be r over y, cosine will be x over r, secant will be r over x, and tangent, cotangent stay the same. When we do the next section, triangles, they will be defined in terms of opposite, adjacent, and hypotenuse. But for now, we're just going to stick to this. So if we move on to the next slide, we could see the summarize, and this is for points on the unit circle. So they are corresponding to the unit circle. Remember, if the radius is equal to 1, then they will look like that. Sine will just simply be y. Cosine will be x, and I should be saying sine of t, which is the angle, the variable we're using for the angle, and cosine of t is x, tangent is y over x, cosecant is the reciprocal of sine, and then we have here secant and cosine are reciprocals, and so are tangent and cotangent. So when we say reciprocal, we don't mean the inverse or the opposite. We mean reciprocals such as the numerator and denominator switch places. You can think of it that way. So in the definitions of trigonometric functions, note that the tangent and secant are not defined when x equals 0. So I'm going to rewrite those two. So we're talking about tangent, and tangent, I'm going to use the abbreviation, is defined as y over x. And then secant is defined, I like to use parentheses. Secant is defined as 1 over x because it is the reciprocal of cosine. So if x was 0, then you will be, it's like you were dividing by 0. And so that is not possible. We will say, for the purpose of this class, just undefined. And so that means that tangent and secant, if x was to be 0, and that I'm talking about the points that are on the y-axis. So for example, if you remember the way we started labeling our circles, this happened at pi over 2 or 90 degrees. But also it did happen at 3 pi over 2 or 200 270 degrees. So at those 2 points, we will just simply answer and say that tangent is undefined. And so will be secant if x was to be 0, if our point was here or here. And when I say a point, I mean the terminal side of an angle. Then the initial side, initial, and terminal. Or we could have another one starting here and going in this direction, and this will be the terminal side. Okay, so moving on, we already mentioned that, and just to remind you of how the unit circle, this is very useful. If you just plot the points 1, 0, the next point is going to be 0 for the x and 1 for the y. The next point will be -1 for x, 0 for the y, and the next point that is on terminal side will be 0, -1. So based on that, you could determine which ones, if x is equal to 0, then you know that tangent and secant will be undefined. Now, similarly, if cotangent and cotangent is defined as x over y, and we have cosecant, which is defined as 1 over y. So now if y is equal to 0, it will be like you're trying to divide by 0. So therefore, those two will be undefined. If y was equal to 0. So that will happen here and here. And just to refresh our memory, that could be at 0 radians or 0 degrees, and also at 2 pi radians or 360 degrees. And it could also happen if we go from here to here, and that will be pi radians or 180 degrees. In figure 4.17, the unit circle is divided into 8 equal arcs corresponding to t values of, so the degree measurements will be equal to 0, pi over 4, pi over 2, 3 pi over 4. And I just want to point out that if we were to just have a number line that started at 0, and this was pi over 4, and the last one was 2 pi, let's say that. So if I was told to do that same line and to divide it into equal parts, and oh my gosh, I put here a 2, that should have been a 4, pi over 4, and to divide it like that, the next one will be 2 pi over 4. The next one will be 3 pi over 4, and then I will have 4 pi over 4, and then 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, and actually we will stop right there. So I'm gonna just redraw this line. Okay, so it will look like that. Now pi over 4, it's already in reduced form. However, 2 pi over 4, it could be reduced to pi over 2. 3 pi over 4, we leave it like that. 4 pi over 4, it could be reduced to pi. So that's what we're going to use. 5 pi over 4, it is in reduced form. And then we have 3 pi over 2, so that one could be simplified by dividing 6 and 4 by 2, so we get 3 pi over 2. Then we move on to 7 pi over 4, already in reduced form. And then finally we have 8 pi over 4, which could actually be simplified because 8 divided by 4 is equal to 2 pi. So we're going to go ahead and place those t values or angle measurements on our circle. So we start here. This will be 0. Here we will have our first pi over 4. On the next one, it will be 2 pi over 4, but we already agreed we're going to call it pi over 2. And the next one, moving on, will be 3 pi over 2. And the next one is pi. Next one, if pi is equal to 4 pi over 4, the very next one will be 5 pi over 4. We move on to 6 pi over 4, but reduced form is 3 pi over 2. The next one will be 7 pi over 4. And then the next one will be 2 pi if we do complete a full rotation. So what we can see here are the x and the y values for each of those points. And in fact, let's mark this ones. So this is for you to start memorizing the x and y coordinates. And we call this special angles. Okay, so if I was to ask you what is the sine of pi over 4, based on the definitions that we went over previously, that is defined as the y coordinate. So the answer will be the square root of 2 over 2. If I ask you what is the sine of, let's say, 5 pi over 4, that will be the point corresponding to this angle, and the y value is here. So that will be the negative square root of 2 over 2. Now, what if I ask you what is the cosine of, let's see, what do we like? 7 pi over 4. And so cosine is defined as the x coordinate of the point, and that will be here, the square root of 2 over 2. And this is using the unit circle and the coordinates. Next section, 4.3, we will use, we will discuss the same topics but using triangles. So now we're going to do the same. We're going to label some of our common angles. And now we're going to divide the circle into 12 equal parts. So before we place the numbers that we have listed here on the left side of the screen, I'm going to label I call them terminal angles, but they're actually called quadrantal angles. So it will be 0 radians or degrees. This will be pi over 2 radians or 90 degrees. Here we have pi radians or 180 degrees. And here we will have 3 pi over 2 radians or 270 degrees. And then if we go one full turn, this will turn into 2 pi. Okay, now let's start with the pi over 6. which will be the very first one here. And our next number, we're going to do the same thing that we did previously. So here for our number line, we have here pi over 6. This will be 2 pi over 6. And 2 pi over 6, it simplifies to pi over 3. The next will be 3 pi over 6, which simplifies to pi over 2. And in fact, we have that one already there in color green. And then the next segment will be 4 pi over 6. And that one simplifies to 2 pi over 3. And then we have 5 pi over 6. That one is already in reduced form. Then 6 pi over 6. We divide 6 over 6 and we will get pi. That is one of the quadrantal angles. So if we keep going in that way, this will be 7 pi over 6, already in reduced form. Then this will be 8 pi over 6, which simplifies to 4 pi over 3. Then we will have 9 pi over 6, and that one it reduces to and is one of the quadrantal angles, 3 pi over 2. Then we will have 10 pi over 6, and 10 and 6 could be divided by 2, so we will get 5 pi over 3. Then we will have 11 pi over 6. And then, of course, lastly, 12 pi over 6. And 12 pi over 6 simplifies to 2 pi. Okay, so we already have the quadrantal angles positioned there. So let's go ahead and write down the ones that have a denominator of 3, the ones that I have circled with pink. So we will have, and I'm going to just erase this one here. So we will have, or actually I'm going to write it in purple, pi over 6. What else? 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those will be the ones that we will write on purple. So the first one is here, 5 pi over 6. The next one is going to be in pink, pi over 3. The next one, pi over 2, we have it. The very next one is going to be also in pink, and that will be 2 pi over 3. The very next one, 5 pi over 6, that will be purple. And then we have 6 pi over 6, or pi. That one is already there. The very next one will be 7 pi over 6. And remember, this is if we divide the circle into 12 equal parts. In other words, half a circle is divided into 6 equal parts. Then we come to the next one, 4 pi over 3. So I'm going to write that in pink. The next one will be 3 pi over 2. Then we will have 5 pi over 3. And then finally we will have our 11 pi over 6. So now if we put that unit circle and we combine it with the one that we created or labeled here with the pi over 4, with the 3 pi over 2, and I'm going to circle what I'm talking about, with the pi over 4, 3 pi over 2, 5 pi over 4, 7 pi over 4. If we were to put those two together, and then we will have what is commonly known as the unit circle. And of course with the quadrantal angles. So what you can see here is that we are given the x and y coordinates for each of those points. So with the x and y, they are already telling us what is and remember they go in this order. Cosine is the x coordinate, and sine is the y coordinate. So the cosine of pi over 3, if we were to ask that question, will be equal to the x coordinate, which is 1/2. And if we ask what is the sine of pi over 3, then we look at the y coordinate, which is the square root of 3 over 2. And so you can see, just like the circle, some numbers are positive, some other numbers are negative. Just as a quick reference, in the first quadrant, both x and y are positive. Second quadrant, x is negative, y is positive. Third quadrant, both x and y are negative. Fourth quadrant, the x is negative and the x is positive and the y is negative. Okay. So this is a quick way to verify the points on the unit circle in the figure 4.17 are correct, I guess. And note that they also lie on the line y equals x. So that line is the line that we see here. And so if you recall from pre-cal 1, that is the identity function, and we call it the identity function because the input is the same as the output. So if we start with the equation of a circle, which is of the unit circle actually, with the center at the origin at 0, 0, it will be x squared plus y squared is equal to 1. And what we're going to do here, since we're saying that x is equal to y, we're going to replace the y square with x squared because we're saying that x and y are equal. So we get x squared plus x squared instead of y squared equals 1. So I'm just rewriting what is already there. And from here, if we combine x squared plus x squared, we will get 2x squared is equal to 1. If we're trying to solve for x, the next step will be to divide by 2. So we will get x squared is equal to 1 over 2, which is what we have here. And finally, we take the square root on both sides of the equation, and that will give us that x is equal to the square root of 1 over the square root of 2. And what that means is that the square root of 1 is 1 and the square root of 2 is just the square root of 2 because we want an exact answer. Also, we are going to use the plus and minus symbols here to indicate that because the square root of 1 could be 1, but it could also be negative 1 because negative 1 times negative 1 is equal to positive 1. So what I was saying is that the square root of 1 could have two answers, either negative 1, like it was shown to you there, or also positive 1. So that's why we use that symbol. Now, however, we don't want to have radicals on the denominator. So what we do is we multiply by the square root of 2, top and bottom. And so we multiply straight across. So we will get 1 times the square root of 2 is the square root of 2. And the square root of 2 times the square root of 2 will be like the square root of 2 times 2, which is 4. Or you could think of it as 2 squared. And so, of course, the square root and the square cancel each other. And so now we are left with the square root of 2 over. And from here, we still have that 2. And so that is how we get that number for x and how we get that number for y. And also, since we're saying x and y are equal, that's how we determine that x and y are both the square root of 2 over 2. I want to move on to our first example of evaluating trigonometric functions. For this example, we're going to evaluate all 6 trigonometric functions that we already discussed. So we're going to be calculating the sine of pi over 6. So we are, of course, replacing the value of the variable of t with pi over 6. Then we're going to find the cosine of pi over 6. And then also the tangent of pi over 6. Okay, so I want us to look at the circle, and we have it here. So pi over 6 in standard position, it's located, remember, always from the positive x-axis, and the terminal side will be here. So this point corresponds to the angle pi over 6. So remember this the square root of 3 over 2, the x coordinate represents the cosine for this angle. I'm going to just call it t, but we know it's pi over 6. And the y coordinate is going to represent the sine of that angle. So we could see here that sine is going to be equal to 1/2, and the cosine will be equal to the square root of 3 over 2. And that is pretty much all we need to know. So, sine of pi over 6, 1/2. Cosine of pi over 6, the square root of 3 over 2. Now, since the tangent is defined as y over x, we are going to replace that y over x with the coordinates. So we will have for y is 1/2, and for x is the square root of 3 over 2. So in this case, I can multiply the outer quantities. 1 times 2, that is 2, and then 2 times the square root of 3, so 2 times the square root of 3. After that, we could cross out the 2's. They cancel because 2 over 2 is equal to 1. So this turns into 1 over the square root of 3. Now, I'm actually going to write that down here. 1 over the square root of 3. But we don't want to leave radicals in the denominator, so we multiply both top and bottom by the square root of 3 over 3. And that will give us the square root of 3 over the square root of 3 squared, or we could just simply say 3. Okay, and this is the multiplication symbol. Now what we're going to find is the reciprocal ones, and that will be the reciprocal of sine is cosecant. The reciprocal of cosine is secant. And the reciprocal of tangent is cotangent. So this is pretty easy because we know we're going to just interchange the x and the y. So this will be 2 over 1, or simply just 2. For secant, it will be 2 over the square root of 3. So in this case, we do have to rationalize, and we multiply by square root of 3 top and bottom. So we end up with 2 times the square root of 3, and then the square root of 3 times the square root of 3, it will be the square root of 3 squared, which is 3. So this is the value that we will be using. And then finally, we could take the reciprocal of this number, or we could go to the original answer that we obtained from dividing the two fractions. And so if we use this one, it's easier to get the reciprocal of it because it will just be the square root of 3 over 1, or simply just the square root of 3. part B of example 1, we're going to do the same thing, but we're going to use the angle 5 pi over 4. So I want to give you a visual representation of where that angle is going to be located at with respect to the unit circle. And so right here is our first pi over 4. This will be our 3 pi over 4, and here this will be our 5 pi over 4. You could check on your previous slide. And so that will represent an angle in the positive angle, so in the counterclockwise direction. So the point that corresponds to it, and you can look at your notes or rewind this video, and remember for pi over 4, both the coordinates for that particular point were the square root of 2 over 2 and square root of 2 over 2. So the sine and the cosine are the same. So for the point 5 that will correspond to the angle 5 pi over 4, we'll have the same numbers, but both x and y will be negative. So it will be negative square root of 2 over 2 and negative square root of 2 over 2. Okay, so let's do this, and we start with the sine of 5 pi over 4. And so that will correspond to the y coordinate, this one here, negative square root of 2 over 2. Then we have the cosine of 5 pi over 4, and that is also negative square root of 2 over 2. For the tangent, this is the easiest of all, because if we're going to divide x over y, and you see that x and y are equal, so you're dividing square root of 2 over 2 by square root of 2 over 2, and so that will just simply be equal to 1. Now for the cosecant of 5 pi over 4, we will take the reciprocal of this number, but it will still be negative, so negative 2 over the square root of 2. We still have to rationalize, so we multiply by the square root of 2 top and bottom, and that will give us negative 2 square root of 2 over 2. For secant of 5 pi over 4, it will be the reciprocal of cosine, but we already have that because it happens to be the same as the reciprocal of sine, so it will be the same number, negative 2, already in rationalized form. Oh, and I'm sorry, I forgot to see that we have 2 over 2, so that is equal to 1. They cancel out, so the final answer should be only the negative square root of 2. And so for this one, it will be the same thing, the negative square root of 2. So in this case, cosecant and secant are equal. And then if we move to cotangent of 5 pi over 4, that will be the reciprocal of 1, which is also a 1. Part C of example 1, we are, for that part, we're going to use t equals pi. So let's remember where pi is located at with respect to the unit circle. And so that will be equal to 180 degrees. And the point that corresponds to that, if the radius is 1, so we're going in the negative x direction, so that will be negative 1. And the y value will happen to be 0. So based on that, remember the y coordinate is representing sine of that angle, and it happens to be pi. And the x coordinate is representing the cosine. So let's start. So sine of pi is equal to 0, the y coordinate. Cosine of pi is equal to the x coordinate, negative 1. And tangent of pi is equal to 0. Y is defined as y over x. 0 over -1, which is equal to 0. And let's see, for cosecant of pi, we're going to have, imagine the 0 had a 1 on the denominator because it is an integer after all. So if we get the reciprocal of that, we will have 1 over 0. So we're just going to say that the cosecant of pi is undefined. For secant of pi, we will have the reciprocal of -1 over 1, which is still be 1 over -1, or you could call it -1 over 1, or it will just be -1 at the end. And cotangent at pi of pi will be the reciprocal of this number. And so that will be something like -1 over 0. So we will also say that the cotangent is undefined. For part D of example 1, we will be using a negative angle, and this will be -pi/3. So let's try to locate that here. So remember, angles in the negative direction or with a negative sign, they start on the positive x-axis, but they go in the same direction of the clockwise direction. And so pi/3, it will probably have a terminal side ending here. You could check with your notes. And if we, of course, we're talking about unit circle. So the coordinates for that point, let me see if I can remember this. So if this is pi/6, the coordinates there will be 1/2 for sine and the square root of 3/2 for cosine. And so our pi/3 but positive, remember this is negative. This is -pi/3. But if we were to go in the positive direction, it will be here, positive pi/3. And the coordinates there will be 1/2 and the square root of 3/2. And I know that because the x and y are interchanged from pi/6. We will cover that later. So at that point, I can, if I look at the coordinates here, and I want to write down the coordinates for down here in quadrant 4, the x value will be -1/2, but I'm sorry, I keep doing this. The x value will be +1/2 because it's on the right side of the origin, and then the y value is the one that will be negative square root of 3/2, and this is for the negative angle, -pi/3. So I'm gonna, same thing, we're gonna write the trigonometric values. So the sine of -pi/3 will be equal to the y coordinate here, which is negative square root of 3/2. And for the cosine of -pi/3, we're going to have the x coordinate, which is +1/2. For the tangent of -pi/3, we're going to have the y coordinate, so that will be -3 square root of 3/2 divided by 1/2. And that will equal to, if we multiply the quantities on the outside, I like to refer to this as the sandwich rule. Imagine that's the bread. So 2 times the negative square root of 3 will be -2 times the square root of 3 over 2 times 1. So that will be a 2. We cancel the 2's and we will get negative square root of 3. Okay, cosecant is the reciprocal of sine. And so that will be the reciprocal of that number, which will be -2 over the square root of 3. If we multiply by the square root of 3, top and bottom, to rationalize the denominator, we will obtain negative 2 square root of 3 over 3. Now let's work with secant, reciprocal of this one here, of cosine. So secant of negative pi over 3 will be equal to the reciprocal of 1/2, so that is equal to 2. And then finally, we have the reciprocal of tangent, which will be cotangent of negative pi over 3. So it will be the reciprocal of this number, and imagine it does have a 1 for denominator. So if we flip those numbers, it will be 1 or negative 1 over the square root of 3. And we multiply by the square root of 3, top and bottom, to rationalize the denominator. And that will equal to negative 1 times square root of 3 is just negative square root of 3. And then we have square root of 3 times square root of 3 is equal to square root of 3 squared, which is just equal to 3. So there we have it. We have all 6 trigonometric functions for that angle. Okay, so now what we're going to do is define I guess the boundaries of the sine and the cosine function. So far we have mentioned that the coordinates x and y, they are actually representing the cosine for that angle. We're calling it t, and the other one is called sine of t, that is the y coordinate. So for those two, if we were to consider this is a function and this is another function, so we could say that x is equal to cosine of t, and we could also say that y is equal to the cosine of t. Now, we're so used to seeing things like x equals y, or y equals x, or y equals x squared. Now, what we're doing is saying that the domain, which is the input of this function, is going to be t for both. That's the domain. And in fact, t, it could be any real number. It could be positive, it could be negative, it could be, not only an integer or a special angle, it could be any angle. So to determine the range of these two functions, it will be, for the cosine of t, the range, which is the output, in this case will be x. And in the case of, oh, and I have this written wrong. I apologize. This should say sine. For the sine of t, the output or the range will be y, or all the collection of numbers of y. And so if you recall, when we started tracing the unit circle, like the one we have here, we discussed that the radius was equal to 1, and so therefore this line is equal to 1, this line is equal to 1, this line is equal to 1, and so on. So due to that, we wrote our points, and they were all they're listed here. So we do have 0, 1 for that point. We have 1, 0 for the point on the x-axis. We have 0, 1 for the point on the y-axis, and we have negative 1, 0 for the one on the negative left x-axis, and we have 0, negative 1 for the one below the origin. So based on that, we already know the sine, which is all the y coordinates, and we also know, so I'm going to go ahead and highlight all of those. All the y coordinates, that will be all of our sine for those quadrantal angles. And I'm actually going to use a different color here. For x, And so you could see, if we look at the width of the circle, the width of the circle it's actually equal, if the radius is 1, the diameter is equal to 2. But if we are talking about points on the Cartesian plane, we will say that it goes from -1 to +1. That is what we have here. So in this case, we will say the range, which is just being represented by x, it will be the interval from -1 to 1. And for the sine function, the range is going to be the same. If you see, the minimum point happens here at -1, and the maximum point happens here, the maximum y value is at +1. And so this is going to be extremely important when we graph our sine and cosine functions on section 4.5. So with that said, I'm just going to say it one more time. Since in the circle, the x and the y values range from -1 to 1 for both, we're going to say that the values of sine are also going to be between -1 and 1, and also for cosine between -1 and 1, meaning they cannot be 1.2 or 5.9 because that will be above 1. Similarly, they cannot be -10 because that will be less than -1. Okay, so the next concept that we're going to explain is how, if you keep increasing rotations or revolutions, that is going to make you land at the same point. So for example, the angle here is going to be pi over 4. So if we do go and if we just go that rotation, we start at the positive x-axis and we go here, the terminal side will be there where pi over 4 lands. Now if we go one full rotation, so 2 pi, and then we go another pi over 4 rotation, so we go 2 pi full rotation or full revolution, and then another pi over 4. So that number is actually going to be pi over 4, and 2 pi in fourths should be 8 pi over 4. And so that one will be equal to 9 pi over 4. I should have known that. Yeah. So, and if the idea is that if we keep doing that in the same way, we do one circle, then we do a second circle, and then we do another pi over 4, then that will be another, if we have this one and we add another 8 pi over 4, that angle will happen to be 17 pi over 4. So all those angles have the same terminal side, and they are coterminal, and therefore they have the same sine and cosine values. And the same applies to any other angle. For example, here for pi, that will be the angle, just 180 degrees pi. But if we do one full circle and then half a circle, that will give us 3 pi. So same thing applies. So moving on, we could generalize that the sine and the cosine are periodic and they repeat every 2 pi. And just like we used on the previous slide on the examples. So we could generalize it this way. And also that would be just adding one rotation or one revolution, but we could continue adding rotations or revolutions, and we could go in the positive or the negative direction, and they will still be the same. So the n here is just a real number. So n could be, let's say, 1. If n is 1, we will have t plus 2 pi times 1. But if n is equal to 2, then we will have t plus 2 pi times 2, which will equal to t plus 4 pi. So that is what the n is representing. And of course, n could also be negative. We call this behavior cyclic, or periodic, and it's a repetitive behavior. So the definition of a periodic function, like it says here, is where there exists a positive real number c such that the function of t plus c is the same as t. In this case, our number c is represented by 2 pi because they repeat after every 2 pi radians. Okay, the next table is even and odd trigonometric functions. I don't know if you recall something from pre-cal 1 that said that if f of negative x, if you substitute it and you get the exact same thing as the original function, you call that even. And if you substitute negative x, replace it for the x, and you end up getting not the original function, but the complete opposite of it, then you have an odd function. So this is what we're saying here, but we are using t instead of x. Okay, so for cosine, cosine happens to be an even function. And so that happens when you replace the x with a negative x and you get the exact same function. So that happens to cosine and also to secant, because remember they're related, they're reciprocals of each other. Now, on the other hand, we have that sine. Sine of negative t is equal to the negative sine of t, so we say that they are odd. And if sine is odd, so is cosecant. For tangent, same thing. Sine is odd. I'm sorry, tangent is odd, and cotangent is also odd. And this is important because it tells us the graph, the behavior of those graphs. Not of the unit circle, but of some other graphs that we will be graphing in section 4.5. So using the concept of periodic tables, functions, we're going to say that the 13 pi over 6, if we were to ask what is the sine of 13 pi over 6, I will tell you that it is the same as the sine of pi over 6. And that's actually my favorite because it's so easy, and that is 1/2. How do I know that? Well, because we have 13 pi over 6, which could be broken into 2 pi plus pi over 6. For part B, negative 7 pi over 2, we're going to break that into negative 4 pi plus pi over 2. To show you that it is true, we could combine those terms. So negative 4 pi over 1 plus pi over 2. And that could also be, if we multiply this side, this fraction by 2 over 2, we will get negative 8 pi over 2 plus pi over 2, and that gives us negative 7, negative 7 pi over 2, which is what we had over here. Now, how do we know to break it into negative 4 pi and then pi over 2? Well, because remember that periodic functions will be defined as if t, let's say sine of t, will be the same as the sine of t plus 2 pi. And moreover, we said that that could be extended into multiples of 2 pi, and we were using the letter n. So in this case, the letter n is actually negative. So n is negative 2. So this was t plus 2 pi times negative 2. And so that was t plus negative 4 pi. So any multiples of 2 pi, like 2 pi, 4 pi, 6 pi, 8 pi, but also in the negative direction, like negative 2 pi, negative 4 pi, negative 6 pi, they will work. And so the sine of this function, negative 7 pi over 2, is the same as the sine of pi over 2. And remember, that was that point that is located here with the coordinates at 0, 1. So the sine is 1, the y value. And if we want to go ahead and write the cosine of negative 7 pi over 2, it will be the same as the cosine at pi over 2, which is given here by the number 0. And here cosine of 13 pi over 6 is the same as the cosine of pi over 6, which it happens to be the square root of 3 over 2. If you don't remember, don't worry, you will remember by the end of the summer. Just check your notes. Okay, and finally here we have sine of t equals 4/5 and the sine of negative t equals negative 4/5. And the explanation for this is that sine function is odd. So that goes like this: sine of negative t is the same as the opposite of sine, but with the positive angle. So that will be the 4/5, but with the negative sign in front of it. So that is the answer to this question. So the sine of negative t. Okay, if the question was what is the cosine, then the cosine of negative t will be the same as the cosine of positive t. So moving on, last thing I promise. Sometimes there are angles that we cannot get by using that method that we've been using, so we have to rely on calculators, and that's why you need to have a calculator, and I do need you to get a graphing one, so I want to remind you of that. I'm not gonna cover this right now because I would like to show you with the calculator, and I will do that tomorrow during the live session that we're having as the lab for this class. So this is the end of the video. Thank you for watching.